Howdy. So it's 9 o'clock, so we're going to go ahead and jump into things. There's a lot of content to cover, so I'm going to kind of be like Micro Machine Man here, speaking really fast, trying to fit everything into 45 minutes. But first off, just thank you for showing up. When I kind of saw my time slot and right before the keynote, I thought maybe I'd done something really horrible to the scheduling people at some point. But I'm really relieved and happy to see a bunch of you here because it would have been kind of anticlimactic to do all this prep work and have no one show up. So yeah, the standard lawyer thing. Title page, me. Some of you know me. I guess most of you don't. I'm a sustaining engineer. I spend most of my time, my day job, fixing hotspot bugs. And I have Twitter and a blog. And yeah, that's me. So today we're going to focus a lot kind of on the history of mission control, where it came from, just to give us the big picture and some perspective. We're going to go over how to download and build it yourself and just kind of show you how easy that is to do on your own. And then just because it is a GUI tool, and it would just break my heart to kind of talk about a GUI tool for 45 minutes and not show anything off or do a demo, we'll actually kind of just show a really neat aspect of flight recording that people might find interesting. And then we'll finish things off with a summary. So first off, kind of obvious to anyone that's looked at the schedule, but we're suffering from an embarrassment of riches in terms of content. So if you'll notice, of all these different mission control sessions, I don't know how readable this font actually is, but we have a number of them are actually delivered by Marcus Hurt, who everybody who knows mission control is going to be familiar with that name. So Marcus and Clara Ward, obviously those sessions are going to be really worth seeing if you're a fan of mission control, and I can't recommend them enough. Also, we have a session from my coworker Poonam, who's on the hotspot sustaining team with me, and her sessions are always very good and highly recommended. I mean, I recommend all of them, but if you have to pick any, I think the top 4 are probably going to be maybe the best bang for the buck. So some background here, we're going to be covering a number of things. The title of the talk was Mission Control, and that's kind of what's gotten the most attention, but really there's just a number of very closely related technologies, and it doesn't make too much sense to talk about one without the other. It's kind of like the killer app, like talking about Diet Coke without Mentos. If Mentos didn't exist, why? People buy it, for other reasons, but I'm not entirely sure why. And in the same sense, not quite as drastic, but the real killer app for mission control is Flight Recorder, and so that's what we want to focus on and talk about. So Flight Recorder support came to Oracle JDK, or the commercial JDK builds that we do all the way back in JDK 7, and it's just very recently been open sourced in JDK 11, and this explains kind of this huge influx of interest and participants who are using it and even contributing source code back to the project. So Flight Recorder, just to make sure everyone's on the same page here, it's basically this framework or this technology to both generate and persist JVM level events during runtime, and it's extremely low overhead. So the idea is that in many situations you can just have it on all the time in production because the cost of it is so low. So it kind of serves the purpose of like a flight recorder, a black box in an airplane or something, where after something bad happens or something goes bump in the night, you can go back and look through the history and try and figure out what happened. So mission control is a tool that's used to visualize the flight recording data that you've collected, kind of for offline analysis. But it also has some other functionality. There's a JMX-based console that allows you to connect to a target JVM in real time and look at the data directly. And it also features a plugin framework, so there's other things like JOverflow and whatnot that allow you to do things like look at heap dumps or whatnot. That can be convenient. So there's a number of different things that you can do that are kind of related functionality that are all available within the tool. And then the tool itself, because it's based off of the rich client platform, can actually be integrated into your Eclipse IDE. And there's a whole lot of really neat functionality where you can do things like jump to individual lines and source code files and stuff like that you wouldn't get if you were just using the client GUI application on its own. But like I said earlier, the real focus, the real bang for the buck is really using it as a flight recorder visualization tool. So if we're going to talk about the history of flight recorder and mission control, we have to go back all the way to Sweden. So originally there was a company known as Appeal Virtual Systems. They actually had a number of different names. At one point they were trying, I think they actually had like a music in the name somehow. They were trying to be able to write off buying instruments and stuff like that. But there were a bunch of guys that had all gone to school together, and they founded a company, and they were doing a lot of Java-based consulting work for clients. And somehow that turned into eventually writing their own JVM. And this JVM was known as JRocket. And unlike some of the other JVMs or Hotspot, it didn't have an interpreter. It was a JIT-only JVM, which kind of made a whole lot of things much simpler. You didn't have to worry about things like de-optimization and stuff like that, because there was no interpreter to fall back to. Things were either JIT compiled or really optimized JIT compiled, and that's the only two flavors that things came in. So it kept life simple, and it was a really performant implementation, especially on Intel architectures. So it originally was marketed as this quote unquote virtual machine for Java, not a JVM. And the reasoning behind that is to get an actual proper Java license from Sun, you had to say that you had a quote-unquote value add. You had to bring something new to the Java ecosystem or cover some sort of gap that wasn't there before. So for most vendors, it was obvious they were just porting Java to a new platform, and that was a very easy to understand value add. But JRocket was supporting platforms that more or less was already covered by Sun or maybe other providers. And so originally, I guess they responded that superior performance. Our JVM performs better than Hotspot, and that didn't go over very well with the people at Sun. And so kind of as a take two, they went back and said, well, we also have this monitoring functionality that we can bring to the table. And so it's that additional monitoring functionality that became eventually evolved into these tools like mission control and what would eventually become flight recorder. So we have, if you're keeping track, from Sweden, they've invented styrofoam, whatever this is, and a flight recorder. So they're on a roll apparently. So we have a pair of Appeal Virtual Systems, and very soon after they did succeed in getting a Java license from Sun Microsystems, they found that in order to kind of grow their business and move to a global scale, they needed a partner, and so they ended up being purchased by BEA Systems, who was looking for its own JVM vendor to kind of compete with the other J2EE application server vendors at the time, so that they could offer a full stack offering, so customers had a single neck to wring when things went wrong in the night. So JRocket and its associated technologies became part of BEA Systems, and then of course more things happened. It wasn't quite like that. Yeah, that's how it was. Yeah, that would be what it looked like. And so things happened, and then more things happened. And so it eventually, the JRocket people and the Sun Hotspot people, even though they had competed against each other for a very long time, ended up kind of working on the same team, definitely working on the same team. And a lot of these technologies ended up getting merged. And so even though JRocket itself, no longer really exists in any kind of usable form, the legacy of JRocket, a whole bunch of things that JRocket pioneered got brought over into the Hotspot world. And so, for example, the JCMD commands, the diagnostic commands that we all know and love that got introduced in JDK 7, and new commands get added every single release. But that whole framework, the diagnostic commands framework, came from JRocket. The compiler control commands that were added in JDK 9 that allow you to do things like be very specific about excludes for JIT compilation and really drill down into a level of detail you couldn't do with the earlier command line compile commands. That came from JRocket. Native memory tracking came from JRocket. Of course, flight recorder, obviously. And behind the scenes, the build system was almost completely rewritten by one of the ex-JRocket engineers. And around this time, the JRocket Mission Control was renamed Java Mission Control. You'll notice this theme kind of repeated later on as well. So going back, so during this whole period of time, over a decade, there was an evolution of Mission Control. Actually, I mean, there was a GUI tool before Mission Control, but basically I couldn't find any really useful pictures of what that looked like. So we're going to start off with Mission Control 1 here. But there was a number of associated technologies that were related, sometimes integrated into the GUI, sometimes as a separate tool that you would launch. For example, there was what we call the memory leak detector that would allow you to connect to a JVM in real time and try and kind of pull heap dump-like information out of a live running system to do debugging as you're actually, as the state of the heap is changing, which was really interesting and not something that we have today in the hotspot world yet. But the really interesting thing is this JRocket runtime analyzer, which is what would eventually evolve into flight recorder. So the runtime analyzer was basically what they had come up with after their experience doing all this consulting work, where they found that it's really good to be able to cast this really huge net when they're trying to diagnose performance problems. So instead of using all these individual tools that might get little pieces of information, that if you can just collect a whole bunch of different information from all the different subsystems of the JVM and then look at it as one solid thing, 9 times out of 10, you can kind of find the direction of where your investigation should be going. And so that really cuts down on the number of iterations that you have to do with a customer, because if you just start off with getting a recording, then that 9 times out of 10, you're gonna at least have a clue of what's going on overall. Okay. And what was really neat is that you didn't really have to pay a high price for collecting a lot of this data, because this data was already stuff that the JVM internally was collecting for its own uses, whether that be heuristics or whatever. So for example, if you're doing a mark and sweep over the entire heap, during the mark phase, you're going to collect naturally all sorts of statistics, or be able to collect a whole bunch of statistics about the state of the heap. So why not utilize that data to persist it in some way, and then afterwards you can analyze it to learn things about the way your application behaves. So this original implementation, the JRocket Runtime Analyzer, would dump the data as XML, and it would just zip it up into a zip file. So that was the output, which you could imagine was probably not the most efficient way to persist this stuff. We had a few kind of evolutions of the GUI tool. But then after the Oracle acquisition, the first and final version of JRocket that kind of came out, as an Oracleized product, introduced a new form of this tool or technology, which was known as the flight recorder. And the difference between flight recorder and the JRocket Runtime Analyzer is that the whole back end was basically replaced, and we were no longer using XML to persist stuff, but we had our own proprietary binary format. That was much smaller, and so it was much more efficient to hold it in memory in per thread buffers in a global buffer, or persist it to disk. Whatever we were doing with this data, it just took a whole lot less space, and so it was a whole lot less costly to manipulate it and to hold on to it. And so all of a sudden, Flight Recorder went from the JRocket Runtime Analyzer, where if you were having some problem or you're investigating something, you would take a recording of this data, to something that had such a low overhead that we could just have it on all the time. And that was really the idea behind it when we went to market with it. Around this time, the GUI tools that were visualizing this data also were evolving, and so Mission Control 5 was released. And Mission Control 5 is significant because Mission Control 4 was significant because this is the first version that was post-Oracle, and so this is the first version that supported what we called Flight Recorder. So then after JRocket was kind of put to pasture, and it was clear that whatever the future was, it was going to be based off of Hotspot, those hot JRocket technologies like Flight Recorder were brought over. And the first version of Mission Control to support flight recorder and other hotspot functionality was Mission Control 5. So there's a break here where 5 and later versions are hotspot specific, and then 4 and earlier versions are completely JRocket specific, and there's really no compatibility or overlap between these versions. So flight recorder finally came to hotspot in 7U40. And the idea is that we were trying to make the migration of JRocket users as nice and pleasant as possible, so that they didn't feel like they were losing any kind of functionality. That said, there was a time period where we were just adding more and more flight recording events. And so almost every major release, certainly every major release, but even update releases for a while, we're getting significant new functionality in terms of what kind of data they were recording with flight recorder. At this time also, Mission Control became bundled with the JDK. So when you download it, you also had Visual VM and a whole bunch of other tools, but Mission Control became one of the other tools that was included by default. And so there's this loose correspondence between Mission Control versions and JDK versions as to what was bundled. And while there's always this attempt to maintain backwards compatibility, so with Mission Control 6, you could open up flight recordings that were recorded with all the earlier versions of the JDK. The opposite is obviously not true because the format was changing. And so generally speaking, you would always want to be using the latest Mission Control, regardless of what target JVM you were actually trying to monitor or analyze. So then the really big change was, a few years ago, Mark Reinhold announced that, in addition to this change in cadence for releases, that we were going to open source pretty much all of the closed source technologies that were part of the hotspot ecosystem. And that, of course, included both the flight recording implementation that was built into hotspot and the Mission Control tools that were used to look at that. So this new open source version is actually licensed under a not too well-known license, though it's the Universal Permissive License, but it does offer some nice things. I have some experience with this license because we moved the HSDIS disassembler plugin for hotspot to this license. And when we did that, the feedback we got from the community, specifically the OpenJDK community, was very, very positive. So my personal experience with this license has been pretty good. It seems to make a lot of people happy. I don't want to go into too much detail because I'm not a lawyer and Oracle hates it when we talk about licenses. But I would want to direct people to, there's an FAQ about this license that kind of really explains things in a very easy to understand way. And there's a link to that at the very end of this slide deck. They say it can be used as a contributor agreement, but in this case, that doesn't apply to Mission Control. For Mission Control, if you want to contribute code and kind of take part as a participant, you have to sign the Oracle contributor agreement. This is just like any other OpenJDK project. And so, you don't have to do it per project or anything like that. If you've already signed the OCA for other OpenJDK projects, then you're covered for Java Mission Control and vice versa. So I just want to point out, just because the Universal Permissive License can be used in some context as a contributor agreement, we don't do that at Oracle. So Mission Control and the related flight recording technologies were open sourced, and we immediately had a whole bunch of participation, and significant. The number of contributors was significant, especially from certain companies, and the feedback that we received was very positive. Specifically, we had this comment in the alias from what was ostensibly one of our competitors in the Java space, commenting, Marcus, on how good of a job he had done at making it an inclusive community and really making it this transparent, open project that is kind of an ideal open source implementation. I've already talked about compatibility a little bit, but just to reiterate, because this is a very important point, is that the later versions of Mission Control are backwards compatible with the earlier flight recordings. And so generally, we always recommend that you just use the latest version of Mission Control, whatever that may be. Today, as we talk about it, it's basically 7 or some build of 7. And so, moving forward, we want to see everybody, regardless of which JDK you're using, kind of migrate to the open source, quote unquote, modern mission control versions. So that said, building, let's look at how difficult or easy this is to do. It's actually very, very easy. Marcus has a page on his blog that walks you through it, but it's so simple I can just go through it in 1 or 2 slides. What's impressive is that, especially on a Linux distribution, you can really build it almost out of the box. Mercurial and Maven are, of course, extremely popular tools, obviously Maven more so than Mercurial, but these are popular enough that they're in the repositories for most major distributions. So if you're starting off with like Red Hat Enterprise Linux 8, you can just do a yum install or whatever and grab Mercurial and Maven and then grab a JDK from Oracle's download site and you're ready to go. So setting up a build environment is trivial. So when you actually want to get the source code, there's 3 repositories. The mainline dev one, the latest code, is just in JMC. There's a branch that's broken off for JMC 7, and then there's a separate repository for graphic resources and images and things like that. So there's also a GitHub mirror. It doesn't seem to quite be in sync with the other stuff, and it also only really has the mainline dev version. And so while at some point, everyone's talking about Project Scar and they're very excited about that, but as of today, right now, the definitive repository is still the Mercurial repositories. And so my recommendation is if you're downloading and building mission control for your own use, is that for now you stick to the quote-unquote official repositories. Especially if you're only cloning a repository, you can just kind of squint your eyes and pretend like Mercurial is Git, and it won't hurt you. So building, like I said, is really, really simple. We're going to do it right here, but you just have to open up 2 shells. So that there's one where we're setting up a P2 repository that the build process in the other shell is going to access. And so it's literally just, you could cut and paste these into your, into your 2 shells after you sync everything down, and you're good to go. So in one shell, we're setting up the provisioning platform, which is basically just an OSGI specific repository where the Eclipse components are set up and made available over a network connection for the build process that's run in the other shell. So let's see what that actually looks like, just to show you how ridiculously easy it is. So I have on the left-hand side, I'm setting up the P2 one, and anybody that's paying too much attention here will maybe say that I'm cheating because I've downloaded all this stuff ahead of time before I ran it. Like I've run the Maven command before. I don't know how exactly what the unit of measure is for how much data Maven downloads when it's building something, but I assume the most reasonable unit is maybe like Libraries of Congress worth of data. So several of those get downloaded, but then after you do that the first time, as long as you don't do a clean, that will stick around. And then subsequent builds are very quick and very easy. So right now on the left-hand side, we're just waiting for the P2 instance to pop up, and it will in a second. While we're waiting for that to happen, though, we can kind of continue going through our slides. Sorry. So at the end of this process is that we'll actually end up with bundles for all 3 of the major target platforms, which is Mac OS, Windows, and Linux. And so basically, you can call it cross-compilation. The idea is that the RPC, all the platform-specific bits are pulled from the net. And so the mission control itself is really kind of like a pure Java thing. And so we're not really cross-compiling, but all the platform-specific stuff, all those dependencies get pulled down. So when we're done with this build process, like say we wanted mission control to run on Windows, I could choose to do that build on Linux just because Linux is easiest and I'm closest to building it right out of the box as soon as I turn the machine on. And then I can use those builds on whatever platform I want. So let's look at how this is going. So you can see here where it says started Jetty server. So this basically is my indicator that I'm good to go in the other one. So now I'm just running several commands from shell 2, and that will take some time, but when we check back, it'll pretty much be done. And this also runs a whole bunch of tests and stuff too, so it's actually a very, very fast build. So that said, so now we're going to jump into kind of a demo. I just really wanted to show off how cool Flight Recorder is, because a lot of the neater details of it sometimes go unnoticed, and people don't kind of realize how amazingly awesome and useful it is. But to explain this demo, I have to kind of go through and do some background, which also allows me to touch on a whole bunch of JVM internals, which is always fun for me. So I'll talk about safe points. Just to get an idea of what my audience is, how many people here know what a JVM safe point is? Okay, so maybe about 2/3, a lot of the audience. So, but for the people that don't, and for the people that do, to review here, just to make sure we're all on the same page. So a safe point is basically how we implement stop the world. So when we need to stop the Java execution threads, because we're going to do something like, the textbook example is obviously a garbage collection. We need some way to be able to signal threads and let them know that they're going to stop. And so you can think of it as kind of as a handshake. In practice with Hotspot, what we've generally done is we do this across the entire JVM, and so all the execute threads are eventually stopped. And when those threads stop, we need to make sure not just that they're not running, but they're stopped at a place that we know something about. We want some corresponding metadata so that we can tell that, you know, if a thread stopped and we're looking at its stack in memory, that we want to know what positions in the stack are actually pointing to heap addresses, because that's going to be how we're going to pick up our routes for garbage collection. Or if we're doing bias revocation for lazy unlocking or something like that, where we need to go through and look for lock tokens in a particular thread's stack, you know, we need the thread to actually be in a known state. And so what a safe point is it's kind of two things. It's a mechanism for stopping threads at these locations, and you can also think of them as individual locations in the code that when we JIT compile code, we need to make sure that we have certain places that are safe points to stop at, where it's like, it's okay for you to pause here. This is where we want you to check and see if we want you to pause, and then if that flag is set, this is where you stop. So this is kind of like a cooperative suspension mechanism, where it's up to the thread on its own, in most cases, if it's running native code, to stop when we need it to stop. And if that doesn't happen because of some sort of bug or something, then that can actually hang the entire JVM, because we end up waiting forever from thread to end. So if you're having horrible memories from, you know, Windows 95 or something like that, where just one rogue application could basically bring your whole system down because you didn't have preemptive multitasking, this is kind of like that. But because we implement how all the threading, you know, is done. And so because we are doing it, we can be sure that we're doing it correctly, or hopefully we're doing it correctly. And, you know, in practice, there aren't really many bugs related to safe pointing, so it generally works. But it's dependent, especially for JIT compiled code, on polling. So each thread has to proactively go out and say, hey, you know, do you want me to stop? And the way that this is implemented, well, for interpreted code, this is really easy, right? So the threaded interpreter in Hotspot is basically going through a jump table constantly. So it uses every single implementation for each bytecode instruction basically has at the tail end of it a lookup of the next bytecode, and it pulls the address it should jump to out of a jump table. And so what we do if we want to stop the interpreter is we just replace that jump table with another table that has all addresses that basically have the code to shut the thread down and stop it. So we can stop a thread between any two bytecodes in effect, and that's very easy, and it's very cost effective because the thread's not proactively doing any work to check some flag or something. We just go in and change one global pointer that is used as the lookup table for its jumps, and then we can stop the interpreter. But for compiled code, it's much more complicated. So for compiled code, what we do is we have a single page in our address space, and that address space, it doesn't really matter if there's any data there or anything. The important part is the permissions that are on that page. And so by changing the permissions on that page, we can force threads to stop. So what happens is that compiled code will go and look at that page, it'll try and read that page. And if the read succeeds, then that means it had read permissions to access that memory, and then it just goes about its way. It doesn't actually care about what the data it's reading. All it really cares about is that there wasn't an error when it tried to read it. But say we're going to collect a thread dump, and so we need to stop the world. We need to pause all the threads. So what we'll do is we'll use, on Linux, mprotect, and we'll change the permissions on that page. And we'll say, okay, now everybody that tries to read from that page will get a SIG V. And then our own signal handler comes in for each individual thread and then stops it and says, hey, here's where you're supposed to stop. Here's the condition of the thread. And kind of reports back to the JVM through a handshake. So it's a fairly complicated process, but it works really well and it's extremely performant. What's interesting here is that means that when we compile code, we have to pay attention to where we're going to put these safe point pulls in. We can't just have them in every other instruction, because that would be a lot of overhead, and that would be unacceptable for JIT compiled code that we want to run as fast as humanly possible. So, we put polls. JRocket used to put polls in the beginning of method invocations. Hotspot, for whatever reason, does it at the end of invocations. The Azul one also does it, seems to do it at the beginning of method. In the method prologues, that's one place we do it. So anytime you call into another method, you get a save point. Anytime you call into the JVM, there's another save point. And then for most loops, anytime we have a back edge where we're jumping to an earlier location, we're also going to put a save point in there. So if you're stuck in a loop for a long time, you don't freeze up the JVM. So this is where we're going to go on kind of a weird tangent here, and I want to introduce the Collatz conjecture. Does anyone know who this is, know what this is, or heard of this? So it has nothing to do with Java, but it's one of the unsolved math problems, and it's something that I thought, I can't just have something that counts, because that would be so boring and horrible, and no one wants to sit through looking at a demo like that. So what this does is there's this algorithm that you apply, and the Collatz conjecture is that if you follow these rules, if you follow this algorithm, you will always end up basically going into a loop where you end up at 1 eventually. And so the idea is that this is true for all positive integers, but we don't have a mathematical proof for that yet. So this is an open problem in mathematics. And it's kind of an interesting one. If you go check it out and spend some time, it's really easy to kind of fall into a hole where you're just like, I'll prove those math weenies and show them a computer science guy can figure this out, and lose a few weekends that way, or so I've heard. But anyway, so this is just some examples. So the rules are very, very simple. Basically, if you have an even number, then you just cut it in half. If you have an odd number, then you multiply it by 3 and add 1. That's it. That's the whole thing. And so the idea is that the conjecture is that you'll always end up at 1 eventually if you start with any positive number. So let's look at some examples. 2 is an even number, so we cut it in half. We're at 1. 3 is an odd number, so we multiply it by 3, which is 9, and then add 1, then we're 10. And then 10 is an even number, so we cut it in half. So you can see this pattern. And so each kind of run, depending on the number we start off with, will take a certain number of iterations to arrive at 1. But so far, as long as we've tested, and people have tested all the way up to, basically the 64-bit integer space, more or less, we've seen that this conjecture always seems to hold true. And there's what's known as the trivial conjecture loop, where it's like 4, 2, 1, will repeat. So from 1, we'll multiply that by 3 and add 1, you're back at 4. And so this loops, but there's no other loops out there that don't include 1. So there's this trivial loop, but the idea, another way of saying the conjecture is that there are no other loops besides this, in effect. And this gives you some really interesting, convergent behavior that you wouldn't necessarily expect. So here we're plotting the number of iterations that it takes to stabilize and to go back to that original trivial loop where you're back at 1. And so sometimes it can take many, many, many iterations, even for very low numbers. But it's kind of got that aspect just like prime numbers do, where there's this emergent pattern or behavior that people don't necessarily understand or explain, but it gives you, kind of pretty pictures. So let's get back to Java. So let's test the Collatz conjecture the stupidest way we can possibly imagine. Again, this is just to kind of show off safe pointing and what Flight Recorder allows us to do. But so if we're going to implement this in Java, the rule is very simple, right? So we can get this in one line if we want to make our code, kind of a pain to read. Right here, we're just checking if it's even, and then if it's even, we divide it by 2, and if it's odd, we multiply it by 3 and add 1. So this just takes one 64-bit integer and gives you the next 64-bit integer, and that's all this code does, and it's really small. It's the kind of code that an optimizing compiler would, of course, inline into anything that it's running. You would never have this as a separate thing that you would call. So what we have here is this kind of main program that calls next. And we have 2 loops here. On the outside loop here, we're going from 2 to integer max value. So these are, of course, signed integers because it's Java, so that's like 2 billion-ish, let's say. So we're going to go through about 2 billion different possible numbers, and these are the starting numbers of each chain that we call the next on. And then we have another loop in here, an inner loop here, and this is obviously a little bit contrived. I wouldn't write code like this normally, and that's why this is kind of ugly, but to kind of prove the point here, so I have another for loop in here, and we're basically going through and calling next up to 2 billion times if it requires that much. And as soon as we eventually end up at a 1, we'll break out of this loop. And so it's just 2 loops in here, and both of them are basically based off of an index that is a simple integer. And for each iteration of the outer loop, if we actually find that we went through 2 billion iterations of the algorithm and we still aren't at 1, then that would be kind of an interesting result, right? That would be like, hey, maybe the Collatz conjecture is wrong and we found a counterexample. Now we know that's not actually going to happen with numbers this small, but we want to check it just to make sure, right? And then if not, then we just keep continuing on the loop. But every million iterations we go and we print something out just so you know that it's still doing stuff and it's not sleeping or anything like that. So this brings us to what is known as a counted loop. And a counted loop, this is a hotspot specific term, but this is basically any loop where we're basically incrementing or decrementing an integer index, and so a 32-bit number. And so the idea here is that with a counted loop, your worst case scenario is that you could be in that loop 4 billion times. So if you started at like -2 billion and you counted up to 2 billion, positive 2 billion, you have about 4 billion iterations, which for modern computers, depending on what's in the body of your loop, is not going to be that long. If you're just like incrementing something, some counter or something, that's going to happen in less than a second, right? So, for counted loops, the idea is that we don't need to put safe point polls into counted loop implementations when we C2 compile them because, worst case scenario, it's a second, right? But if you look again at the code here, the body of this counted loop has another counted loop in it. So our worst case scenario here is 2 billion times 2 billion, depending on how long it takes us to break out of each individual chain of the Collatz algorithm. So this could be a very, very expensive, and of course it is a very, very expensive calculation to do. So where are our safe points in this code? Well, because these are both considered as counted loops up through at least JDK 8, there are no safe points in here. So this will just keep running. And so this thread will kind of turn into a rogue thread that could keep the JVM hung where it's not responding to signals or anything, and you can't collect a thread dump indefinitely, except for the fact that every million iterations we stop and we print something, and every time we call out into native code or we have any kind of jump over the Java JNI boundary here, that's of course going to be a safe point by definition. And so we do have safe points that are coming, but this is about like maybe every second or so. This will pop up when we're actually running it. So let's look at what this actually looks at. And just to return, well, that's horrible. Okay, so I thought I downloaded the dependencies and I didn't. So because I don't have a network connection that's working, the build failed. I tested this in my hotel room like about 2 hours ago and it worked. So I don't know what I did wrong here, but take my word for it, it's really, really easy to build. Right, Marcus? So yeah, if you come to my hotel room, it's really easy to build. That sounds way sketchier than I planned. No, no, no. Okay, so let's go back to the demo. Okay, so I'm going to go here, and I'm running Java 8 here, and so I've got the loop going. And so let's ask ourselves what a normal traditional sampling-based profiler, how that would handle it. So I'm going to use Visual VM. This will take just a little bit of time. So Visual VM will have difficulty even connecting to this process because, again, when the system's trying to save point, all the other threads are like, yes, I'm done, I'm in a good place, but, I don't, there's one thread that the JVM will still wait for. And so doing things like trying to connect using the attach API or something can be delayed. So here, I'm going to go ahead and select sample. Can people read the display here? It's not ideal, but you'll see here that it's actually taking time to connect here. But it will eventually, or if it doesn't, I have a really nice screenshot that I can show you. But most of the time, it succeeds in actually connecting here. So we can wonder what we're going to expect to see from a traditional profiler. And again, we're looking at this is just the source code for that, for the demo that we're executing right now. And you can see, so all the work really, or most of the work is going to be here, right? And intuitively, that's what we believe or are going to assume. This is where the algorithm's being run mostly. And again, any optimizing compiler worth its salt is going to inline this. And so that should be right inside of this. So, okay, so we finally connected. We're kind of warming up, so to speak. So come on, give me sampling inactive. All right, so now I'm using traditional safe point-based profiling. Now, of course, there are two kinds of profiling, right? There's sample-based, and then there's sampling-based, and there's invocation counter profiler, or stuff that's based off of instrumentation, where we go through and use bytecode buggery to go in and insert invocation counters and things like that. And the problem with invocation counting is that you have this observer effect where you're actually changing the performance characteristics of what you're trying to measure. And so in practice, we've always found that sampling-based profiling is the ideal way of doing things, because even though you don't have exact invocation counts like you do with bytecode instrumentation, you do know that, just generally speaking, heuristically, well, we seem to be in this method 10 times more than this method, so maybe our optimization efforts are going to be better spent there. So again, let's look and see. Okay, we didn't get data on this time. I have a slide with what this will look like. Sometimes it does fail. Again, I think it's just because it's really hard to kind of get data over the attach API when the JVM is stuttering. So Visual VM, when it does succeed, it kind of looks like this, and it tells us, well, we're in main. And of course we're in main, because that's like the only method in the source code except the next method. And the next method is going to be inlined by the compiler. So this tells us, look, we don't have any line numbers, we don't have any bytecode indices or anything. This gives us no useful information. So let's look at what Flight Recorder does. And I already have, just because we're out of time, I already have the recordings that I've done here already saved. So we're just going to look at those. So here I'm firing up Mission Control 7, which again is extremely easy to build. It's just a matter of maybe 10, 15 minutes after you sync everything out from the repository. And so I'm going to go and I'm going to open running this exact same program. And we had here the automated recording analysis is running, but we're going to jump right to method profiling. And we can see here it's like, oh, well, we were in the colette's loop, and it's giving me some line numbers, so it's a little bit better than what we had with Visual VM. But it's also not great because, again, it's that next method. That's where we're doing all our work, or at least looking at the source code, that's what we expect, and we're still in main. So what are we missing here? And what we're missing is the fact that we don't, even though we can stop things without a safe point, we don't have any metadata for those positions. So we can asynchronously stop a thread and look at it, and from its instruction pointer tell what method it's executing, but we don't know how that maps back to Java code at all. So what we want is the C2 compiler to actually go in and give us more metadata than it would normally do. Normally this would be wasteful, right? But if we're actually going and trying to profile stuff, we want to know exactly which bytecode index, and by extension that will give us which line number, if we have that debug information in our class file, everything corresponds to. So let's look at a recording that is taken with that extra information. And you can see here, sorry, this is, by far, how do I maximize this? You can see almost all of our sampling counts are here in the next thing, and it's actually giving us line numbers, which we can verify. How do I shrink this? Again, against our source code, so we know that it's in line 21, and it'll even allow us to drill down in the user interface here, and I can say, go down to the bytecode index if I was interested in which part of this. So I could look at the Java P output for this particular class and see, where I'm spending most of my time. So that's just a really cool thing that technology like Flight Recorder allows you to do that other profilers just don't support. So this is the conclusion of my summary slide. So the open sourcing of Mission Control has been a fantastic success. We have a lot of people and a lot of companies that are interested in contributing significantly. Our recommendation is we want everyone really to move to Mission Control 7 or later. That's really where the future is these new open sourced versions of Mission Control, and that's where all the excitement and energy is being poured into. We hope to have our own binary builds of Mission Control for people that don't want to build it on their own, available from Oracle at some point in the near future. I know this has taken a little more time than we originally expected. These are not technical problems, but just kind of internal process issues that we've had to deal with. But we believe that we're kind of through the tunnel and see the light at this point, and we hope to have something very soon for that. And then Flight Recorders, the internal API that we use in Hotspot called Async at Trace, allows you to do some really cool profiling that just other profiling technologies, monitoring technologies just don't offer. So thank you for showing up before the keynote. I'm honored to have you all here, and I really enjoyed talking to you. Thank you very much.